lecture we look at some optimization based methods for cell formation. So far we have seen a few algorithms to create part families and machine cells, starting with the production flow analysis. We also looked at rank order clustering, we looked at similarity based approach or a hierarchical clustering based approach, and then we followed it up with a non hierarchical clustering based algorithm. All of them provide good solutions to the cell formation problem, but we address another issue of, is there scope for optimization, or how does an optimum solution to this problem look like, how does an objective function look like for this problem, and so on. So, we will be looking at a couple of optimization based algorithms. Let us revisit the grouping problem that we have already seen more than once. So, let us go back and look at how we group. Let us say we have 5 points which we call as 1, 2, 3, 4 and 5. Now, let us go back to the non hierarchical clustering algorithm, where we said that we want to have 2 groups and we pick seed points. Now, let us say that we want 2 groups. We have already seen that one of the ways of getting 2 groups is to have 2 seed points, and we have already seen that it is good to have the seed points as the points themselves, and we have seen that the seed points should be far away from each other. Now, for this simple example, we know that if say this S1 and S2 we could do to get the best group. In fact, even if we had tried this as S1 and this as S2, we would still have got the same groups at the end of the exercise. We also know that if we had tried this as S1 and this as S2, we will not have got a very good solution, because if we had tried this as S1, let us look at the yellow solution where this is S1 and this is S2. So, if we had S1 S2, by which I mean 2 is seed S1 and 5 is seed S2, if I group with this, one would have gone to this. Let me remove this for a moment. So, 1 would have gone to 2, 2 would have gone to itself, 5 would have gone to itself, 3 and 4 would have gone to 5. So, the groups would have been 1, 2, 3, 4, 5, but distance would have been D12 plus D35 plus D45. This would have been the distance, because D22 is 0 and D55 is 0. If we had chosen this one, or before that if we had chosen this as S1, this as S2, now for this solution the distance will be D12, which is the same as D21, D11 is 0 plus D34 plus D45. If we had chosen this, then the distance would be D13 plus D23 plus D54, because 3 would be 0 and 4 would be 0, 5 would have gone to this, these 2 would have gone to 3. Obviously, this is a bad solution, and by judging either from the points themselves or by understanding the value, this is not a good solution, because this value is large compared to either this or this. Now, even though both of these would give the same groups 1, 2 and 3, 4, 5, can happen that one of them is slightly smaller than the other. Therefore, one of the ways of solving this problem optimally is, if there are 5 points in this case, 2 seeds can be chosen out of 5 points in 5C 2 ways, and for each pair of seeds starting from 1 2, 1 3, 1 4, 1 5 up to 4 5, 5C2 is 10. So, 10 such solutions. One can do the clustering, get the groups, and more importantly get the total distance, which I call as sigma dij, total distance. For example, for the combination 2 and 5, for 2 and 5 somewhere, this would be the yellow one, D12 plus D35 plus D45. Compute all of these and then choose the one which has minimum distance of these, that would certainly give us the best group. For example, there could be many which would have given us this, there could be many pairs of seeds that could have given us the solution 1 2 3 4 5. 1 3 would have given that, 1 4 would have given that, 1 5 would have given that, 2 3 would have given that, 2 4 and 2 5. Actually 6 out of these 10 pairs would have given us the same groups 1 2 and 3 4 5. But 1 out of the 6 or more than 1 out of the 6 would have the smallest distance. So, certainly the one with the smallest distance will give us the best solution. So, if we are looking at an optimization problem, the criterion to choose would be minimum distance, would be to minimize the distance. So, the optimization problem will look like choose 2 points and cluster around them. A very rudimentary algorithm would be to choose all possible pairs, cluster around them, find out the distance as an objective function or a measure of performance of the cluster, and choose that pair of seeds which has minimum distance, that pair of seeds and the associated groups that has minimum distance. Now, that can be formulated as an optimization problem with an objective of minimizing the distance. So, given a distance matrix, given a distance matrix, get points 2 out of these 5 and take it. Now, there are several ways of formulating this problem, one of which is a well known formulation. So, we will do this formulation and then we will go back and explain and name the formulation. So, the formulation will be like this. Now, we could say that we want 2 seeds. So, we could either say that if point j is a seed, we could say yj equal to 1 if point j is a seed. Now, instead of saying yj equal to 1, we now say xjj equal to 1 if point j is a seed point. We could have defined it as yj, but we simply define it as xjj equal to 1 if point j is a seed point. equal to 0 otherwise. And there are 5 points, there are going to be 2 seed points. So, there are going to be 3 non-seed points. These 3 non-seed points are going to be assigned to seed points, and these 3 are the ones that are going to create the distance that we have here, because assigning the seed point to itself gives a distance of 0. So, xij equal to 1 if non-seed point I is assigned seed point j. So, a non-seed point I has to be assigned to a seed point j. So, we have written the decision variables equal to 0 otherwise. Here I can write equal to 0 otherwise, again equal to 0 otherwise. So, what are my constraints? Sigma xjj equal to p, j equal to 1 to n summation. Now, here n is the number of points that I have. So, there are 5 points 1, 2, 3, 4 and 5. So, I want 2 out of the 5 points to be seed points. So, x11 plus x22 plus x33 plus x44 plus x55 equal to 2, where p is the number of groups that I want. So, sigma xjj equal to p. Now, at the end of the day we are going to form groups. So, each point out of these n points should get assigned to one group. The seed will get assigned to itself, the non-seed will go to one of the seeds, but every point will have to be allocated to a group. So, that is given by a constraint sigma xij equal to 1 summed over j for every I. Every point I has to be assigned to a group or to a seed. So, that j represents a seed as well as a group. I is always a non-seed. So, each I will go, including j, including itself will be assigned to a group. The last one is that if, for example, 1 and 4 are seeds, then 2 has to be either assigned to 1 or assigned to 4. It cannot be assigned to 3. It cannot be assigned to a non-seed. So, this constraint will take care of that, xij less than or equal to xjj. For every ij, for every ij. Now, let me explain all of these again. If we consider a solution, say with 1 and 4 as seeds, then for this solution x11 equal to x44 equal to 1, they are the seeds. So, sigma xjj equal to p is taken care, we need 2 groups. So, 1 1 and 4 4 is equal to p. So, it will not create a third seed, it creates only 2 seeds. This is one of the solutions. Now, 2, 3 and 5 are the non-seed points. 2 will get attached to 1 or 2 will get attached to either 1 or 4. Now, what is this constraint? This constraint is x21 plus x22 plus x23 plus x24 plus x25 equal to 1 for a non-seed point 2. So, 2 will get attached to either 1 or 2 or 3 or 4 or 5, that is what this will ensure. But then we know that 2 is a non-seed point, and for this solution 1 and 4 are seed points. So, we can have either x21 equal to 1 or x24 equal to 1. We cannot have for this solution these 3, but then we cannot write this formulation specific to one set of choice of seeds, we have to make it generic. So, we also write xij less than or equal to xjj, which means you have x21 less than or equal to x11, x22 less than or equal to x22, x23 less than or xij less than or equal to xjj, x33, x24 less than or equal to x44, x25 less than or equal to x4, x55. These are the 5 constraints corresponding to this for non-seed point number 2. Now, out of these xjj's, for any feasible solution only 2 of them are going to take value 1. In this example 1 and 4 will take 1, so this will be there, these 2 will be 0, these 3 will be 0. Therefore, 2 cannot be assigned to 2, 2 cannot be assigned to 3, 2 cannot be assigned to 5. 2 can be assigned to either 1 or to 4, and since we are going to minimize some distance, it will go to the nearer one between 1 and 4, so it will go to 1. So, this is the combination of all 3 of them. Now, the objective function will be to minimize So, the objective function is to minimize I equal to 1 to n, j equal to 1 to n. So, now if we have 5 points here, n points, we also observe that by now we have n square decision variables, I equal to 1 to n, j equal to 1 to n, n square decision variables, out of which only n out of the n square decision variables will take value 1, because if a particular point is a seed, then that xjj is 1, correct. If a particular point is a seed, that xjj is 1, so it will be assigned to itself with distance 0. We explained it for the non-seed. For the seed, you actually do not need an explanation, because if you take in the same example, if you take seed point 1, x11 is a seed. Now, for that you will have x11 plus x12 plus x13 plus x14 plus x15 equal to 1 will be this constraint. This set will be xij less than equal to xjj less than equal to x11, x11 less than or equal to x12, x11 less than or equal to x13, xij less than or equal to xjj, x12 less than equal to x22, x13 less than or equal to x33, x14 less than or equal to x44, x15 less than or equal to x55. If 1 is a seed, straight away this is going to be 1, so this is taken care, all of them will be 0, and this is taken care, 1 is less than or equal to 1, and all of these will be 0, because this is a non-seed, 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 this is a seed, but x14 will be less than or equal to x44. In this case it will become 0 because x11 is also a seed. So this will automatically take value 0. So whether it is a seed or a non-seed, we can explain this formulation. Now there are n square decision variables, so there will be n square terms here, but out of the n square xij's, only n xij's will take value 1. The seeds will be assigned to themselves. So if there are 5 points, 2 of them are assigned to themselves. The remaining 3 non-seeds will go to only one seed, so there will be 3, 1 each assignment. So there will be 5 assignments, there will be p seeds and n minus p non-seeds, there will be n assignments, n minus p plus p, n assignments, even though there are n square terms, and out of these n assignments which will contribute to the objective function, the seed being assigned to itself will contribute a 0, therefore only the non-seeds will contribute a distance. That is why we got D12 plus D35 plus D45. There are 5 points, 2 of them are seeds, 3 non-seeds are contributing 3 distances, and the one with minimum Dij Xij based on our earlier argument will give us the optimum solution to this problem. So this problem is called the p median problem. This is well known in the operations research literature. It is sometimes called as a k median problem, depending on whether you define this as p or k. And this problem comes from location allocation problems, from location theory or location allocation theory. It is one of the important formulations in location problems. But the p median formulation was applied to cell formation by Kusiak in 1987, and now we will see how the p median problem can be now used to solve the cell formation problem. So far we have seen how the p median problem can be used to get groups. We have already seen how through similar examples we have seen how we get groups using hierarchical clustering as well as non-hierarchical clustering. So all we need to do is to construct a distance matrix, which we know how to do. So if we are solving a p median problem for the rows, we construct a distance matrix for the rows and then solve a p median problem, because all of them are fairly straightforward. So let us look at an example to see how we apply the p median algorithm to do this. So whatever we have seen is shown in this presentation. So the p median, the constraints are the same, xjj equal to p, sigma xij equal to 1, xij less than equal to xjj, and xij's are binary. In this slide we have shown the objective function to be a maximization where it maximizes similarity. Here we have shown the familiar formula for distance or dissimilarity, which is the same as n minus similarity, and we could solve a p median problem that minimizes distance. So either we could solve a p median problem that minimizes distance, or we could solve a p median problem that maximizes similarity. So we go back to explain the p median problem using the same incidence matrix, which is a 6 by 8 that we have been seeing for the earlier examples, and we now show the same distance matrix that we used in the non hierarchical clustering algorithm, and we have already shown that the distance between 1 and 2 rows 1 and 2 is 6. So, if we want to apply the p median algorithm to form machine groups, we now compute a distance matrix for the machines and solve a corresponding p median problem. So, if we look at this as our machine component incidence matrix, which is a 6 by 8 matrix, 6 rows and 8 columns, the distance matrix amongst the machines will be a 6 into 6 matrix, which is shown here. So, the p median will now have 36 variables, 36 xij's. So, the p median problem will have 36 variables here. So, 36 variables. Xjj equal to p is one constraint, sigma xij equal to 1 will give us 6 constraints, xij less than or equal to xjj in principle has 36 constraints, but one of which is xjj itself. So, you can remove those 6, there is no need to write a constraint which says x22 less than equal to x22. So, it is generally written for I not equal to j, therefore, there will be 30 constraints. So, there will be 37 constraints, 36 variables, binary variables, and we can solve this for p equal to 2 or p equal to 3 or whatever p that we wish to solve. So, if we solve this as a binary integer programming problem that minimizes dij xij, for p equal to 2, the solution is shown here. The solution is x11 equal to x31 equal to x41 equal to x55 equal to x25 equal to x65 with distance equal to 8 is shown as the solution. Now, from this solution we can go back but please note that this solution is for the machine component incidence matrix, it is not for these set of points. So, from this solution we understand that xjj equal to 1 happens here as well as here, which means points 1 and 5 are the seed points for the given machine component incidence matrix. So, 1 and 5 are the seed points. So, seed 1 and 5 machines one goes to 1, 2 goes to 5. You can see that 1 1, 3 1, 4 1, 5 5, 2 5. Machine 2 goes to seed 5 or point 2 goes to seed 5. So, 2 goes to this, 3 goes to 1, x31 equal to 1, 3 goes to 1, 4 goes to 1, 4 goes to 1, 5 goes to 5, 5 goes to 5, and 6 goes to 5, 6 goes to 5. Now, what is the value of the objective function? Objective function value will be, this will contribute a 0, this will contribute a 0. So, this will be d31 plus d41 plus d25 plus d65 will be the objective function. So, let us go back to the matrix. Now, you realize that d31 is the same as d13 1, d14 is also 1, d25 is 3, and D65 or 56 is also 3 with objective function equal to 8. So, if we solve a p median problem with 2 groups, we get a solution like this 134 and 256. Now, we can apply our part assignment rule to try and get the parts, and when we do that we will get the same previous solution, which assigns 1456 and so we will get 1456 2378 with 4 intercell moves. Now, if we solve a p median problem with 3 groups, now the solution is given there. So, x11, x31, x41, x22, x55 or x52 and x66 equal to 1 with z equal to 5. Now, for this, for 3 groups, the seeds are 1, 2 and 6, 1, 2 and 6, 3 to 1. So, 1 to 1, 2 to 2, 3 to 1, 4 to 1, 5 to 2 and 6 to 6. So, once again we can apply the part assignment algorithm to see what happens. Part 1 goes to 1, 3, 4 and 6. So, part 1, this is parts, parts, parts. So, part 1 goes to 1, 3, 4 and 6. So, part 1 here 1 intercell move. Part 2 visits 2, 5 and 6. Part 2 will come here 1 intercell move. Part 3 visits 5 and 6. So, part 3 will go here or it can go here, there is a tie. So, it will go to the smallest cell. So, part 3 will come here, there is 1 intercell move. Part 4 will go to 1, 3 and 6. So, part 4 will go here 1, 3 and 6. So, 1 intercell move. Part 5 will go to 1, 4 and 5. So, 1, 4 and 5, part 5 1 more intercell move. Part 6 is 1, 2, 3, 4, part 6 will be here 1 more intercell move. Part 7 is 2, 5, 6. So, part 7 1 intercell move. Part 8 is also 1 intercell move. So, there will be 8 intercell moves for this solution. As the number of groups increases, generally the number of intercell moves will also increase. So, we may use this solution, but then we understand that if we look at this, we very quickly understand that this is better than this. There is more intercell moves and so on. So, this is how the p median algorithm can be used to solve this problem. Now, the same p median algorithm can be used to solve the part families problem. We showed how it is used to solve the machine cell formation problem by considering a distance matrix for machines. Similarly, we can compute a distance matrix for the parts or components. Now, that will be an 8 by 8 matrix, and the p median formulation will have 8 into 8 64 decision variables, all of them are binary. The number of constraints will be 1 plus 8 plus 56 which would give us 65 constraints for the part families problem. Now, depending on the value of p, we can find out number of part groups and which part belongs to which part group, and then we could go and assign the part groups to the machine groups themselves. But we consistently use our part assignment rule. Once the machine groups are formed, we can use our part assignment rule to try and get the best assignment of part families. Usually in a machine component incidence matrix, the number of rows will be less than the number of columns, which reflects the practical situation that the number of machines that are taken for cell formation will be fewer than the number of parts that are available. So, a p median problem for machines will be a smaller sized optimization problem compared to p median problem for parts. So, it is advantageous to solve the p median problem for machines. Depending on the number of groups that we want, depending on p, we solve it and then use the part assignment rule to assign or allocate parts to known machine groups. So, this way we can solve the cell formation problem as an optimization problem. Now, there are a couple of issues with respect to the p median problem. The first one is that the number of groups is not known a priori. So, while p median can solve it very well for a given p, this particular formulation of p median does not treat p as a variable. It treats p as a known given number and solves the problem for a known instance of p. Subsequently, there were formulations in the literature where p was also taken as a variable and people tried to solve it by treating p also as a variable. Now, we are not going to look at those algorithms in this lecture series, but one of the limitations of the p median algorithm, the way we have applied it to cell formation, is that it expects us to give the value of p. If we do not know the value of p, or if we want to find out the value of p, then we have to solve for p equal to 2, 3, 4 up to n minus 1 and then choose the best. Now, even for a known p, the problem is a binary integer programming problem with 0, 1 variables, and the problem is a hard problem. As the problem size increases, it will be difficult to provide a good solution within reasonable computational time. Another way of looking at the p median is actually p median tries to find out the optimal selection of seeds, and once the seeds are selected, assigning the non seed points to seed points is a simple algorithm. So, the whole focus of the p median is in trying to find out the optimal combination or the optimal set of seeds. So, if there are n points and if we want p groups or p seeds, then they can be chosen in NCP ways. So, in the worst case, p median looks at NCP ways of choosing the seed points. Now, NCP gets large as n is large and p tends to n by 2. So, once again p median problem is a difficult optimization problem to solve. The other issue to be looked at when we consider p median for cell formation is, given a p, let us assume that we can solve the problem optimally. Let us say we can solve the given instance optimally. Now, for a given p, it provides an optimal solution to a grouping problem where the n points or n machines are grouped based on the objective of minimizing the distance. Now, the other question is, now is minimizing distance it is certainly related to minimizing intercell moves, because minimizing distance maximizes similarity and maximizing similarity in a way reduces intercell moves, but maximizing similarity reduces intercell moves when parts are assigned to machines. Now, machines are assigned to machines, which is what p median does by looking at it as a clustering problem. Now, is the objective of minimizing total distance, or does the objective of minimizing total distance adequately represent the important objective of minimizing intercell moves in cell formation, is another question, which p median will not answer, because as a model p median is created to minimize total distance. Now, p median also solves the cell formation problem in two stages. When I say cell formation problem, I mean forming the machine cells as well as forming the part families. So, either p median solves it in two stages, which is solving the machine group formation problem separately, solving a part family problem separately, and then mixing them together by assigning the correct part family to the correct group, or the approach that we have followed by solving the machine cell formation problem separately and applying the part assignment rule to assign parts. So, next step in optimization is, can we overcome these two and look at an optimization algorithm which explicitly considers minimizing intercell moves and is capable of forming machine cells and part families concurrently and not sequentially. So, that leads to the next formulation that we are going to see under the optimization approaches. Now, let us define decision variables x I x I k equal to 1 if machine I is assigned to group K. Let y j k equal to 1 if part j is assigned to group K. So, now we have I is the number of machines. We say I equal to 1 to m, there are m machines. J equal to 1 to n, there are n parts. K equal to 1 to p, there are p groups. Now, these are the decision variables. So, if there are m machines, n parts and p groups, this will be m into p, this will be n into p, because each part goes to only one group. Now, each machine has to be assigned to only one group. So, sigma x I k equal to 1, k equal to 1 to p. Each machine will be assigned to only one group. If there are two groups, machine number 1 can go to either group 1 or group 2. So, this will be a constraint x11 plus x12 equal to 1, and both are binaries. Similarly, yjk equal to 1, k equal to 1 to p for each part j. Of course, xik and yjk are binaries. Now, what is the objective function? Objective function is to minimize inter-cell moves. Now, when do we get an inter-cell move? If we go back to this, when we go back to a solution 1, 3, 4, 2, 5, 6, if we go back to a solution like this, and if we take part number 1, part number 1 visits machines 1, 3, 4 and 6, 1, 3, 4 and 6. So, part number 1 goes here. Now, there is an inter-cell move. What is the inter-cell move? Between part 1 and machine 6. So, there is an inter-cell move if there is a visit between part j and machine I, and part j and machine I belong to different groups. If part j and machine I belong to the same group, and if there is a visit, then there is no inter-cell move. So, inter-cell move comes when part j requires machine I and parts j and machine I belong to different groups. So, minimizing inter-cell move is like looking at an objective function like this, which is to minimize xik minus yjk absolute value aij summation. So, if a particular aij is 1, if a particular aij is 1, only then inter-cell move can happen, may not happen. If a particular part does not visit a particular machine, there is no question of an inter-cell move. So, aij should be 1 for an inter-cell move to happen, and machine I and part j should belong to different groups. So, when machine I and part j belong to the same group, then xik and yjk will be 1, both will be 1, and the difference will be 0. If they belong to different groups, then this will be 0 and this will be 1, or this will be 1 and this will be 0. So, the absolute value term is a difference between a 0 and 1. It is either a 1 minus 0 or 0 minus 1, and the absolute value will give us 1. So, that 1 when multiplied by the incidence 1 will give us an inter-cell move of 1. For example, in this particular instance that we just saw, when we wrote the machine groups 1, 3, 4 and 2, 5, 6, when we wrote 1, 3, 4 and 2, 5, 6, and when we assigned part number 1 here and said there is an inter-cell move happening, the corresponding solution would be 1 is equal to 1, x 1 is also 1, x part 1 requires 1, 3, 4 and 6. So, x 1 is 1, x 3 1 is 1, x 4 1 is 1, x 6 2 is 1 in this solution. Machine 6 goes to cell 2. So, if we go back to this objective function, you now see that there is an incidence between 1 and 1, but x 1 is 1, y 1 is 1, so 0, no intercell move. There is a visit between part 1 and machine 3, y 1 is 1, x 1 is 1, no intercell move. There is a visit for part 1 and machine 4, 1, 1, so absolute value subtracts, no intercell move. But there is a visit for part 1 on machine 6, so there is a 1 here, there is a 2 here, which means x 1 is 0. So, there will be a contribution, so it will add 1 to the intercell move. So, intercell moves are calculated this way. The only difference between what I have written here and what you see on the slide is a half. Now, that happens because it is counted twice, because of the absolute value term it is counted twice, therefore, it is good to write minimize half into this. We also know that multiplication by every term multiplying it by the same number does not make a difference, but we still write the objective function as minimize half into this summation. So, this is the objective function that minimizes intercell moves. This makes sure that each machine and each part goes to only one cell, and these are the binary variables. So, xik equal to 0 1, yjk equal to 0 1. So, this formulation will minimize intercell moves for a given number of groups. Now, this formulation needs to be further looked at. This formulation is from Bachter 1991. This is a binary variable formulation, but something needs to be done because an absolute value term cannot go directly into a formulation. So, we have to make it linear, and we will see how we do that and how we solve the cell formation problem by linearizing it. We will see that in the next lecture.